Hello, and this time I'm going to do a very quick bit of circuit analysis, assuming that the source in the circuit is a cisoid. You may remember that for nodal analysis we use Kirchhoff's current law, and Kirchhoff's current law says that the net sum of all the currents flowing into a node is zero. Or, as I've mentioned, I find that easier to remember in terms of the current flowing into a node is equal to the current flowing out of the node. If all our sources can be expressed in terms of cisoids, then the voltage sources can be expressed in this form here, where V0 is the amplitude of the cisoid, and theta is the phase of the cisoid at time t equals 0, when this term just equates to 1. The same is true of currents. We know that resistors obey Ohm's law, and that tells us that the ratio of the voltage across the resistor to the current through the resistor is constant and equal to the resistance. And that is equally true for cisoids as it is for real voltages and currents. The real usefulness of cisoids starts to become apparent when we consider capacitors and inductors. Because for a capacitor we have this formula. The current is equal to the capacitance times the rate of change of the voltage. And that useful property of the cisoid comes into play here. The differential of the cisoid with respect to time is just j omega times the cisoid. So we can relate the current through the capacitor to the voltage across the capacitor as the current equals j omega c, and j omega c is constant, times the voltage. So we've got something that appears to behave like Ohm's law. The current is proportional to the voltage. And for inductors, similar idea. We have for an inductor, the voltage across the inductor is the inductance L times the rate of change of the current through the inductor. But if the current through the inductor is a cisoid, that's just equal to j omega L times the current through the inductor. So once again, something that looks like Ohm's law. The voltage and the current are directly proportional to each other. And we can just use the techniques of nodal analysis exactly as we did for DC circuits. A quick reminder, because this is important. Resistors obey Ohm's law. The voltage across a resistor is proportional to the current flowing through it, and the constant of proportionality is the resistance R. When I talk about AC circuits, I tend to use the word impedance rather than resistance. Resistance refers to a real quantity, whereas the effective resistance that capacitors and inductors have when there are cisoidal oscillations in the circuit, they tend to be complex numbers. And the term impedance includes the complex and imaginary components. So for capacitors, we have the result that the current as a function of time through the capacitor is equal to j omega c times the voltage across the capacitor as a function of time. And if these are both cisoids, then that gives us the result that the voltage across the capacitor is 1 over j omega c times the current through the capacitor. And if you compare that to Ohm's law, V equals IR, you can see that the capacitor is behaving like a resistance, but the value of the resistance, or impedance, since it's imaginary in this term, is 1 over j omega c. For an inductor, we have the result that the voltage across the inductor is j omega L times I of t. In other words, it's behaving like a resistor, but with an impedance this time of j omega L. To see how this works in a circuit, consider the example circuit on the slide here. Now, this is a current divider, and we could analyse it using the current divider equation. But I'll do it here using nodal analysis to show the technique. Applying Kirchhoff's law to this node in the circuit up here, the total current flowing into that node is 2e to the j omega t. So the two currents flowing out, which will be the current through the capacitor and the current through the resistor, must add up to be this current flowing in. I'll call them IC, the current through the capacitor, and IR, the current through the resistor. And they're both functions of time, so I could write them like this. If I choose to define the voltage at the bottom node here as my local reference, or 0 volts, then the two other equations I need relate the voltage across the capacitor to the current flowing through it, and the voltage across the resistor to the current flowing through it. Well, for the resistor, it's quite easy. That's just Ohm's law. The current through the resistor is going to be the voltage at this node here, which I'll call V out, since that is the voltage being measured by the voltmeter, divided by the value of the resistance, which in this case is 5. And for the capacitor, I can use exactly the same technique. I just have to use this complex impedance of the capacitor, which in this case works out to be minus 5J. So, for the current through the capacitor, I could write that as V out, which is the voltage across the capacitor as well, divided by the impedance of the capacitor, which is minus 5J. If I substitute these current values into this Kirchhoff's current law expression up here, that would give me 2e to the j omega t equals V out over minus 5j plus V out over 5, which is V out 1 over 5 plus 1 over minus 5j. And therefore, V out is going to be 2e to the j omega t divided by 1 over 5 plus 1 over minus 5j. And here, as with a lot of AC circuit analysis, it really helps if you have a calculator that can deal with complex numbers. Because then I could just write 2 divided by 1 over 5 plus 1 over minus 5j. Oops. Yeah. And find that the result is 7.07 with a phase term of minus 45 degrees, which means that the angle on the Argand diagram would be down here. That's minus pi over 4. Pi over 2 is 90 degrees, that's pi over 4. So I would write this as e to the minus j pi over 4 times e to the j omega t, that term there. And that is the cisoid that would appear as a voltage across this voltmeter. As we've seen though, the problem with this is that cisoids don't exist in the real world. You can't have a voltage source or a current source in the lab which generates a cisoidal voltage or current. This is because imaginary currents and imaginary voltages are not real. They don't exist. In the next talk, I'll go over how we can use this technique to analyse real voltages and currents, and a few shortcuts we can use to make that process much easier.